Okay, I got cut off, but fortunately I was cut off right after this. So if I started something else in the last video, I'm going to continue it now. Okay, so this should be reconciled with the Pythagorean theorem, as I think I said at the end of the preceding video. Okay, now we want to prove a couple more things. Okay, so let's go to this. I said, okay, the distance between A1I plus B1J plus C1K and A2I plus B2J plus C2K is this. Well, I want you to prove that. I want you to be able to prove that. You simply write out what it means to do this one minus this one and apply this definition. And everything works out, and you see that you have this. So this is an extension of the Pythagorean theorem to 3 dimensions. It works just fine. And it extends, once you see this, you can understand that it's going to extend to any number of dimensions. You're just going to get a lot of squares under here if you got a lot of dimensions. Okay, so we want to confirm, first of all, I want to prove that the distance between U and V is never negative, because the distance can't be negative, but we've defined it in terms of a dot product, so we want to be sure that it conforms with our intuition, and that the distance really isn't ever negative. So first of all, we got to wrestle with the idea, well, is it even always defined? Okay, we've said that this is the distance, we've defined it, but we never really said that our definition makes sense. If, for example, well, the distance is defined in terms of ultimately square root, right? Well, that square root can't be defined if the thing inside of it is negative. So how do we know that this thing inside of the square root is never negative? Well, we can see it pretty directly. If, for example, in R2, if UV is, if the vector U is A1I plus B1J and V is A2I plus B2J, then you would have things under your square root like A2 minus A1 squared, okay? And all those things are squares, so they're never negative. So when you define the distance from U to V, you always get a sum of squares. You got them here, you got them here, and you'll always get them. And squares are never negative, and you're always adding these things, so they can never be negative. So that's the first observation you want to make. Now, I want to say the distance of UV is greater than or equal to 0. Okay? Well, that follows from what I just said. You're adding up a bunch of squares and then taking the square root. So you're taking the square root of something that can't be negative. So the distance is always greater than or equal to 0. We get that just by considering whether this thing is always defined or not. Then, how could we get 0? Well, the only way we can get 0 is if all these squares, whatever number there are in whatever dimension of the space, if all these squares are 0, because if at least one of them isn't 0, then since they can't be negative, we're going to have at least that value, okay? If the 43rd square is not 0, okay, then it doesn't matter what the other 46 are in 47-dimensional space. You're not going to be able to get 0. Okay, so that's really the essential thing that we want to understand. If U equals V, then of course every one of these is going to be, it's going to be like A1 minus A1 squared plus B1 minus B1 squared and so forth. The A1 and the A2 will always be the same if U is equal to V. So, it's very obvious if U equals V, you're going to get 0. Now, if you got 0, I say U must have been equal to V. Okay, now that's a different statement. We know if U equals V, you're going to get 0, but if you got 0, does that mean that U had to be equal to V? Well, you want to think about that. Okay, I'm not going to tell you. And actually in the other series of videos, we do address that in n-dimensional space. Okay, another one is u dot v equals v dot u. Okay, now can we prove this? Well, that's actually very easy to prove. In R2, it would be u1, u2 times the row u1, u2, and I probably don't want to have a comma in that row. Actually, I do decide to keep the comma in there, just so you don't confuse this. Where'd my yellow chalk go? Just so we don't confuse this with a matrix with columns u1 and u2, which is what it would be if we had arrows over these u1, u2, v1, v2. Since there are no arrows, these are just plain numbers. We don't really need the comma, but I'm going to put it in there as a reminder. Anyhow, multiply this row by this column. Okay, that would be u dot v, wouldn't it? And then v dot u, well then the v1, v2 is your row, the u1, u2 is your column. So verify, what is this? What do you get when you multiply the left side? What do you get when you multiply out the right side? Are they the same? If they are, that proves that the dot product is commutative, and it is, in fact, so. Okay, now, had a couple of other boards that we needed to go over, and I don't see them, so we're going to stop here and continue in the next clip.